Okay, so solving equations is something that most people that are algebra people, this is something that they are really good at. But they don't really think through the rules at all. They just go through and do this. So let's look at, first of all, what it means to solve an equation. Okay, so when you're solving an equation, you're just isolating the variable. What that means is you're getting the variable alone on one side of the equation. So let's get this. Okay. So 14 minus 4t equals 16 minus 2t plus 2. Okay, so we're going to go through and solve this, which means we're going to get t by itself on one side of the equation. So the first thing we need to do is move by term. So a term, once again, we talked about in the last video, but a term is anything separated by this addition and subtraction. So each of this 14 is a term. This is 5 terms in this equation. We're going to move any term that is a t term over to this side of the equation. The way that we do that, if you have to think about it, sometimes some of you just do this naturally, but if you're thinking about it, you're actually going to add 2t to both sides of this equation. Because negative 2t plus 2t is 0. And then that gives us our 2t on this side of the equation, and it eliminates that term from this side. So then the same thing here, where if we want to get rid of this 14, then we are subtracting 14 from both sides. So at this point, so I usually go through, we can go through a slower version, but I would just take, and now subtract, so I'd say subtract 14. I'm going to do them both at the same time, but if you want to do one at a time, that's just fine. I do subtract 14 from both sides. And then I would be able to write my whole expression. So here I have 2t. These 14s cancel each other. So I'm left with 2t minus 4t equals, then here I've got my 16. The 2t's cancel each other, and I'm left with still a plus 2 and a minus 14. Okay, now we go through and we use what we did before, just simplifying the expressions. We take 2t minus 4t to get a negative 2t. 16 minus 14. Or you could, let's go ahead and just do, I always like to take my biggest ones first, but 16 minus 14, just because it's easier for me to do the math in my head, would give us then a 2, and then we add 2 more, so this gives us 4. Now we're going to get t all by itself, which right now, the last thing that we're left with is negative 2t. To get rid of just the 2, the negative 2, and leave the t alone, we would need to divide both sides of our equation by negative 2. So we get t equals 4 divided by negative 2, which is a negative 2. Okay, so that was solving for that, so we know now that the solution to this equation is t equals negative 2. Okay, so just the same thing with inequalities. Inequalities just has one big rule. You have to change the sign of your inequality if you multiply or divide by a negative number. This is my little important sign. I don't know why. I just like to do a little triangle. Just to mark this on the notes like this, or sometimes we'll do like a star. Anyway, when multiplying or dividing each side of an equation by a negative number, the direction of the inequality sign must be changed. Now that is not if you add or subtract a negative number. That is only if you multiply or divide. And so let's look at an example of when we do this, of when that would change. Okay, so let's take 14. Just a second. Let's not take 14. Let's do this one. I was going to do one that I already have worked out. Let's do 5 is less than negative 6 minus z over 4. I try and never make up an equation on the fly when I'm doing these lectures because the answer always comes out terrible. So I go ahead and stick with ones that I've already worked out to make sure that I get one that comes out with an easy answer. So on here, we now have the same thing as we had up here. We're just trying to solve for z. We do have a situation where we need to get z all by itself. So the first thing I'm going to do is I'm going to move this term away from it. It doesn't have a z in it. So we can go ahead and just add 6 to both sides. So I have it, so that should be add 6 to both sides. So then I have 5 plus 6, so I get 11. And this sign stays the same. Make sure you write everything in the same order. The sign stays the same. We get less than. This 6 and this 6 cancel each other, and we're left with negative z over 4. Okay, now the next thing I want to do is get rid of this 4. You can get rid of it at the same time as this negative sign, but let's just take one step at a time. We're going to get rid of the denominator. So what was the opposite, what was the inverse of dividing by 4 is multiplying by 4. So if we take this and we multiply by 4 on both sides of the equation, we get 44 is less than negative z. And this is where now we're going to take to get rid of that negative sign, and we need to multiply both sides by a negative 1 so that we get rid of the negative. So I have negative 1, negative 1. And we get negative 44, and this side would give us z. Okay, now we multiplied by a negative number, and so the sign switches directions. And the other thing is that I personally really like to see z on this side of the equation. So when you switch this, you can switch it, but that is, this points at z, so you need to make sure that it still points at z when you're back this way if you do want to switch it. So technically this would be as far as you need to go. And just make sure that you're really being smart about which direction your inequality faces. And you'll get practice on the assignment with that as well. So you can go through and make sure as you're doing that assignment you're checking the answers and making sure that you are doing it correctly. And if you're getting the signs the wrong occasionally, we need to look and see and make sure that you're not skipping any rules as far as when that sign needs to switch. Okay, the next thing we're going to review is rationalizing a denominator. So rationalizing a denominator, what that means is that you're going to be removing or eliminating radicals from the denominator of a function. So you're getting rid of any radical. So a radical is a square root, or like a cube root even, anything that has that root sign in it. So you're trying to get those roots out of the denominator. A denominator of a fraction must be rationalized for it to be in simplest form, and that's why we always like you to simplify your answers, and the answer is not complete unless you have no radicals in your denominator. Okay, and that'll hold true to all the assignments that you do. You need to make sure that there's no radicals in the denominator. So let's look at an example of how to rationalize. Okay, so we'll start with the basic one. So the square root of 5 over the square root of 2. Okay, so if we want to rationalize the denominator of this equation, we have to get rid of the square root of 2. Well, the square root of 2 means what two numbers multiply together equal 2. So if we multiply this by itself, I'm getting a different color here. If we multiply the square root of 2 by the square root of 2, we get, there's two ways to look at it. One, you can think of it as the square root of 4, which is 2. Or if you multiply the radical by itself, it always gives you the number under the radical. Okay, so this, and by multiplying it, let's talk a little bit more about this for a second too. By multiplying the top and the bottom of the equation by the same number, you have not changed the value. It's like when we talk about simplifying fractions or creating equivalent fractions. It is an equivalent fraction because we've multiplied the top and the bottom by the same number. So here, this becomes 2. And on the top, we use our rules of radicals, which says that we can take these and we can multiply them together. So we get the square root of 10. They're both under a square root. It's kind of like combining like terms, but you do multiply. These are multiplied together, and so you can multiply what's underneath each of those radicals. Okay. Now the denominator is a rational number, and so the denominator has been rationalized because this is rational, meaning it is not a radical. Okay. All right. So, and meaning that it's not an infinite number, it's not a decimal. So it is a rational number, a whole number there. Okay. Let's look at a second example of the same thing. So what about if we take the square root, and we're going to write it a little bit differently, of 18 over 12. Okay, now first of all, the rules of radicals tell us that we can rewrite this as 18 over 12, like this, where each of them have a radical separately. The reason being is we do not need to rationalize the numerator in this situation. We just need to make sure that there is no radical in the denominator. So we look at this and we decide what we need to do. And I'm going to actually simplify this even more first because the radical that we're looking at is even smaller than what we think. So here I'm going to first look at kind of like this where we took 5 times 2 to get the square root of 10. We can separate this out and we're going to call this 3 times 4. Now some of you may be thinking, why are we calling it 3 times 4? Because 4 is a perfect square. So we're looking for perfect squares to come out of it, because then we can take the square root of that, and it will come out of the radical. So 4 is a perfect square. You can find perfect squares by multiplying by a number by itself. Okay, so 1 is a perfect square, because 1 times 1 is 1. 2 times 2 is 4, so 4 is a perfect square. 3 times 3 is 9, so 9 is the next perfect square. 4 times 4 is 16, so 16 is the next. So the nice thing is it jumps up so fast. You're really looking for most of the first basic ones. So we look at 18 and we think, does 4 doesn't go into it evenly. The next one I said was 9, and 9 does go into that. So we want this to be 2 times 9. Okay, now the reason is now we can separate this out. We have the square root of 2 times the square root of 9. And the square root of 3 times the square root of 4. So that now this square root of 9 is 3. Sorry, and I wrote these backwards order. I don't know if that messes anyone up. The square root of 2 cannot be simplified, but the square root of 9 is 3. The square root of 4 is 2. So now this is really what we're working with. So to rationalize this denominator, all we need to do is get rid of that square root of 3 now. So then we multiply the top and the bottom by the square root of 3. And we get, here in the bottom, square root of 3 times the square root of 3 is 3. So we get 2 times 3 left on the bottom. And on the top we get 3 times, and we have the square root of 2 times the square root of 3. So we're left with 3 square root of 6 over 6. Okay, now notice that this still has some reducing that it can do. Everything is multiplied, and so we can divide the top and the bottom by 3. So we have the square root of 6, because 3 divided by 3 is 1 over 2. Okay, so it's a lot of rules, hopefully, that you've been over before. I want to jump back to here and show you what would happen. We can find the same answer. Here, if we would have just gotten rid of the root here. So I'm going to just show you the same way to do, you can do the exact same problem. The only difference is you're going to have a lot bigger numbers. So here, we could have multiplied by the square root of 12 on the top and the bottom. So then we get 12 in the denominator. And then here, we're going to have to do 18 times 12, which is 216. Let's see what happens if you don't simplify it first. These were numbers we all could work with easily. Where here, we're starting to get into numbers where this may be harder to find a perfect square to come out of it. So that's the only difference here. So, I mean, you can do it, and you have to go through and think, okay, that is divisible by 36, and 36 is the perfect square. So you have the square root of 36 times 6 gives us 216. And the only reason I did that so quickly is because I was working backwards because I knew what the answer was. So in other circumstances, that would be a lot slower to try and find what it divides into. You have to go through and try each one. So then we get 6 square roots of 6 over 12. which is the same thing. We can now reduce this by 6. And we get square root of 6 over 2. So it is the same thing. It just makes it easier math if you do it sooner. Okay, so the next thing is that sometimes when we're rationalizing the denominator, there's a plus or subtraction sign. So here, everything was just multiplied. Well, what happens is when we have that, we do need to use what's called a conjugate. Okay, so a conjugate, an example of a conjugate is, these colors are really ugly, sorry. A conjugate would be, if I have, let's say I have the square root of 5 minus, let's do 6 minus the square root of 5. Okay, so ignore this little. So what is the conjugate of this? So a conjugate is when you take the same values, but you do an addition sign instead of subtraction sign, or vice versa. Okay. Now the reason that we use conjugates is because if you multiply by a conjugate, it gets rid of the radical. Okay? And I'm going to show you an example of this, so hopefully that makes a little bit more sense. They're used because the product is always a rational number with no radicals in it. And that's because you create a situation where when you multiply things out, it'll always cancel out the middle terms. And the end terms will multiply by themselves, making it so that it has a rational number. Let me show you with this one first. So let's take these two conjugates and let's multiply them together. Okay, so if I'm going to multiply these, remember that we have, because they're conjugates, we do have to use some people call it the FOIL method. You do need to multiply this by everything in these parentheses and this by everything in this. So we get, first of all, 6 times 6, which is 36, and 6 times square root of 5, which is 6 square roots of 5. Then see what happens when we do a negative square root of 5 times this 6. We get a negative 6 square roots of 5. So every time those two middle terms, if you do your conjugate correctly, they'll cancel each other out. Because you have 6 square roots of 5 minus 6 square roots of 5. And so those will cancel each other. Then we have our negative square root of 5 times our positive square root of 5, which gives us a negative 5. Square root of 5 times square root of 5 is 5. So then we're left with just 36 minus 5, which is 31. Okay, so that was just showing you that conjugates always come out with a whole number. Sometimes they won't be a complete whole number, but the radicals will be gone, depending if there's variables in there. Okay, so let's look at an example that actually uses this as well. So let's say I want you to simplify the fraction 4 divided by 4 minus the square root of 3. Okay. So if we have this, we can't just multiply by the radical because there's the plus and minus there, right? So we need to take this, it's a nice purple here, and we need to multiply the top and the bottom by the conjugate. So the conjugate of this would be 4 plus the square root of 3. And here, the conjugate, still you have to do by the same thing so that you don't change the value of your fraction. You have to make an equivalent fraction here. Okay, so then up at the top we now have, we're going to multiply the 4 times both terms here. So 4 times 4 is 16. 4 times 4 is 16. 4 times the square root of 3 is 4 square roots of 3. And then here we need to make sure we FOIL everything out. So we get 16 plus 4 square roots of 3. And negative 3 times 4, we get negative 4 square roots of 3. And then we multiply the back 2 by each other there, and we get square root of 3 times the square root of 3, which is 3. Okay, now we go through and we can simplify. So here I have 16 plus 4 square roots of 3, which are not like terms. if this had a square root of 3 in it also, you can combine, but it doesn't, so they are not like terms. So that's the top. Now the bottom, the 4 square roots of 3's cancel with each other, and we're left with 16 minus 3, which is 13. 16. We got rid of all the radicals in the denominator, and the equation, or the expression, is now simplified because it has a rationalized denominator.